This is the first introduction to optimization, and we're going to start talking about that. Leave off and talk about something else later. But this first video on optimization concerns. I'll give you a general background, and then we'll look at unconstrained and constrained optimization techniques using traditional methods. So optimization is basically, well, we're all familiar with unconstrained optimization. I'll show it to you. Constrained optimization needs a different approach, and I'll be explaining what I mean by these things in a few minutes. We're looking for the maximum, or this is what I wanted to start saying a minute ago. We're looking for a maximum or minimum of some desired quantity given some function. So we have a function y, say a production function from our other video, right? So the output variable is the objective, and we want to maximize that by finding what input variables will do that, right? What combination of decision variables, the inputs, will give us a maximum value for y. The traditional way, of course, is to take the first derivative, set it equal to 0, and solve for x. Right? That's a very straightforward approach. And that's fine for some things. Often it's not doable, though. We know max if the second derivative is negative, of course, and positive means minimum. So an example, I want to minimize my costs for housing installation, or insulation, excuse me. So what thickness should I use? Well, the objective is to minimize my cost, and the costs, I'll say, are two things, fuel costs and insulation costs. And the variable, the input variable, is the thickness of the insulation. So I know the fuel costs are inversely proportional to the thickness, right? So as I increase the thickness, the fuel costs go down. But of course, as I increase the thickness, the cost to purchase the insulation goes up, right? So the cost function is just this linear combination of that fuel cost and insulation cost as a function of x. And let's say, just for this academic exercise, that K1 is $500. For each inch that I increase, I'll save $500 in fuel costs, say over a year. And then the cost of the insulation itself, say per square yard, is $24 per inch. So I want to minimize my cost for housing insulation. What thickness should I use? Well, here's the objective function, and I want to find the x that will give the maximum value. So I can do the first derivative, set it equal to 0, solve for x. So let's take a look at that. Plot it. If I plot the costs versus the thickness, and I plot the cost of insulation, which we know is a linear function, right? For each inch, it's going to add $24 to my cost. And the cost of fuel, as thickness goes up, fuel goes down, and it's nonlinear, it's asymptotic. So the total cost is the sum of those two. This is the total cost curve. And you can see here the minimum value is right here, right? And it turns out 4.56 looks just about right. So visually you can see that calculation makes sense. So now constrained optimization involves values of x that have constraints on them. And there are two types, equalities and inequalities, and I'm going to look at both examples here. Inequalities are more typical, but not they're not always exclusively inequalities. So the strategy is to transform the objective function so that it includes the constraints. And I'll show you what I mean here in a minute. But let's say, for example, just for concept, we have an output variable y and an input variable x, and I know their relationship, right? So the maximum value for y is here, theoretically, with no constraints. But what if x needed to be less than a? In which case, the maximum value of y would be over here. It wouldn't be over here because we don't have enough x. And that's really what we're doing with this constrained optimization. We're finding this point. Okay, so we're going to use this so-called Lagrangian approach. Whoops, I put an extra n in there. So Lagrangian transforms objective function into the unconstrained form. So we start with an objective function. Let's say we want to maximize y as a function, which is a function of x's. And we know the constraints of the x's. Equal. We're going to do the equals first because that's simpler. And we'll get into the inequalities later. So what we need to do is introduce these what are called shadow prices. These are multipliers that we introduce, and we know there's a set of constraints, right? So we're summing these constraints over however many there are, and we're just taking the difference here. So the trick here is we know, right, from this constraint, it says these two things are equal, right? So the x values need to be equal to a value that will give this difference equal to 0. So we know these are supposed to be equal to 0. Therefore, we know that the maximum of Lagrangian is equal to the maximum of f of x, right? So that's the trick. So let me go through an example here. Let's say I have an objective function here, 6x1, x2, and only one constraint for now, 3x1 plus 4x2 equals 18. Those must equal 18. So the Lagrangian would be then the original objective function minus, we only have one constraint, so we only have one lambda. Lambda times this difference, right, just comes from that constraint rewritten. And the deal here is that if I take the first derivative with the partial derivative with respect to all of the unknowns, I can then solve the simultaneous equations. So if I take the first derivative with respect to x1, set it equal to 0, x2, set it equal to 0, and there's a third unknown that I introduced here, a lambda, and set that equal to 0. So now I have three equations and three unknowns. Pretty straightforward to solve these. x2 is 0.75 x1, and I can then find x1 is 3. x2 is 2.25. Okay, so that's it. So the maximum value then is 40.5 given these numbers. I can move into inequalities. So I have an objective function that max y with some function of x's and a set of constraints that are now less than or equal to. By the way, every time you see an optimization problem with constraints, always convert the constraints to less thans. So, right, okay. And we're going to transform the constraints to equalities. That's the first thing we're going to do. Then we can use what we did before. So if this is a less than or equal to, if I add a positive value to g, I can, a positive variable, I can say it's equal to b. So this variable is squared to make sure it's always positive. S sub I is the constraint I. And then, therefore, I can then just do the same thing. There's the Lagrangian, except now I've got this extra variable in here. So let's do an example. This isn't as straightforward as the other one. So let's say I have a couple of constraints here. And I'm going to transform them. The first step is to transform the constraints. So I'll add this S1 and S2 squared quantities. So they're equal to the constant terms. And then here's my Lagrangian. It's a little longer this time, and I have 1, 2, 3, 4, 5, 6 unknowns. So I can take the first derivative with respect to each of those 6 unknowns. I'll have 6 equations, 6 unknowns. Theoretically, I should be able to solve that. The problem is they're not necessarily linear equations, so it makes it a little harder to find the answer. So you have to use some Sherlock Holmes thinking. So here's the first derivative with respect to x1, x2, s1, s2, lambda 1, lambda 2. And then if we look at these for a minute, we find that lambda 1 cannot be equal to 0, because if it were, 2 would equal 0. That does not make sense, right? So therefore, from this equation, lambda 1 is not equal to 0. Therefore, S1 must be. Right? So just looking at the equations, you can find that. And then down here, if S2 squared is 0, right, then X1 would need to be 4 to make this a true, this equality true. But that's not possible. And let me show you why. I'll go back to, so I'm saying X1 cannot be 4. If X1 is 4, that means this is 9 plus a positive quantity is less than 5. That's not possible, right? So it's not possible. So all the way back here. So in which case, if S2 is not equal to 0, it cannot be, then lambda 2 must be equal to 0. Right? Lambda 2 must be equal to 0. So I can come back up here now. I've found as much as I really need to. Lambda 2 is 0. I can take these first two equations. Lambda 2 is 0. I know that I can solve these and find the relationship between x1 and x2. And from before, I know s1 is 0, so I can use g1 to solve for x1. So if I plug this in to this equation, I know x2 is equal to 2x1. I can solve for x1. It's either 2 or 0, but from lambda 1, it's got to be positive, so 0 is not possible. And therefore, x1 equals 2, x2 equals 4, and the max of the function is 10. Okay, so this kind of lays it out for you for the next week. So I'll be back.